Hey, good morning, everyone. Uh, our class is being recorded now, and I welcome you all to the 11th, I guess, yeah, 11th class of our course on Network Fundamentals for Cloud. Let me just start sharing my screen, and we should be good to go. Right. So we are on this topic of data center networks, and we'll continue with the discussion that we've had. So, what we've discussed so far, a quick recap of the story that we've heard so far about the evolution of data center networks. So, we've started by saying that the older data center networks, they were primarily using layer 2 networking techniques for connecting the server nodes to the rest of the over the rest of the data center network. And the topology followed in the data center network was the access aggregation core topology. But because there were issues that were uh, existing with the layer 2 networks, specifically issues related to broadcast storm, the fact that the blast radius of the network was higher, the bandwidth got underutilized when you used STP, um, and the fact that the network wasn't scalable enough to handle the changing application traffic payload, which was becoming more and more predominantly east-west traffic. The network evolved. In the evolution path, we talked about the spanning tree protocol as the first method to prevent the broadcast storm, but then it had its own limitations with respect to weird configurations that used to emerge in the network topology. We talked about the virtual chassis technology that came in to solve the problems of STP, but that had its own limitations with respect to the control plane getting aggregated into a single control plane, which causes certain other kind of disadvantages and overheads. And then we talked about how L2MP came in, a tunneling technology that worked over a layer 2 network, but could carry traffic over a data center network that evolved to become L2++, right? It had its own um, routing protocol, kind of a uh, OSPF-like routing protocol that came in the data center network, and we talked about Trill as the key technology. In the meanwhile, we are also seeing that the data center network topology is also evolving. So while these technologies are getting introduced in the access aggregation core topology, the data center network topology itself is migrating from access aggregation core to clause because of the advantages that clause topologies give in terms of their scalability and cost economics. So the leaf spine topology is being considered more and more as the topology to be followed in data center networks, or at least the building block for these data center networks. So we talked about how L2MP technologies brought about a key change in the access aggregation core data center networks by introducing the routing technology. And Trill became the most popular protocol. Okay? We looked at how the Trill protocol stack looks like, where Trill itself is a L2++ kind of a network, which is primarily a L2 network, but plus plus indicating that it has routing functionality of layer 3 brought into layer 2. And therefore, any layer 2 packets that are sent from a server A towards, let's say, a server C get encapsulated over a tunneling protocol that takes those L2 packets, which are treated like payloads. This is the L2 packet, by encapsulating it inside a Trill header and then sending it over the Trill network, right? So that's how encapsulation works in L2MP. We noted that there are still disadvantages of L2MP because of the fact that it still relied on VLAN to provide multiple virtual networks for tenants, and that was limited because of the limitation in the VLAN ID. The O&M protocols that are required alongside the key protocol never got evolved. And in the meanwhile, NVO3 technologies came in and they kind of made sure that the L2MP protocol started to lose sheen and lose interest. and therefore the rest of the aspects of the L2MP protocols never got defined. Right? So this is what we had covered so far, and we had said, okay, in the meanwhile, yes, the class topology and its variants had come in, and the DCN protocols started to evolve towards use of L3 technology, the IP and associated networking and control plane protocols that started to come in, and that is where last time we briefly introduced the NVO3 technology, network virtualization overlay technology, which is basically an L2MP like tunneling technology, but something that works over a layer 3 underlay network, which the data center network has evolved. So I wanted to start today with talking a little bit about the case studies that are very important for this part of our course, which I would recommend all of you to read. Of course, I'm not mandating it, the thorough read of it, and I will introduce them in today's class right now as a starting point. But I strongly recommend that if you really want to get deep understanding of data center networks, then these are three uh, extra reading papers or material that I would suggest you definitely look at. Okay, the first is a very generic uh, paper. It's more like a research paper. It doesn't so much talk about any specific Google or Microsoft or Amazon data center network or Facebook data center network. It in general talks about how should one go about designing a scalable and a commodity data center. Right? So what is the scalable commodity data center network architecture? That's what the research paper focuses on. So this is the URL for the paper in case you are interested to read it. Uh, the first section will introduce you to what we've covered in the past classes. It will talk about the changing pattern of the data center traffic, how the applications are evolving to more cluster-based applications, and what it means for the data center network traffic patterns. Right? It's more or less going to introduce you to this topic of east-west traffic replacing predominantly the north-south. That's what we've talked so far as well. In section 2, they will talk about all the general design principles of a modern data center network. So they will talk about how the data center network topologies have evolved. If I remember right, the paper starts by talking about access aggregation core and how it's been replaced by the more modern network topologies. It introduces the concept of bandwidth over subscription. Why is bandwidth over subscription in the data center network cross-sectional area required, right, to prevent congestion in the core part of the data center network and thereby enable faster, low latency communication between the servers to support the east-west traffic. Section 2.2 actually introduces the class network topology. Okay. But one thing that I haven't covered and you might find interesting is we've covered the leaf spine variant of the class network topology, whereas this paper introduces you to another variant of class, which is the fat tree. So we just noted that fat tree is another variant of class networks. Um, Similar to leaf spine, but we did not talk about it. But if you want to know more about it, this paper will help you understand what is fat tree topology and how does it evolve from the classic class network topology. So that's one paper. I'll just say read it more from a design perspective to understand how scalable commodity data center networks are designed and architected. But the papers which actually talk about real life data center networks and how they are designed are the next two, which I'm going to talk about. So the first one is about the Facebook data center network. Okay, so this paper talks about, it's actually a white paper kind of a thing published by Facebook, titled Introducing Data Center Fabric, the Next Generation Facebook Data Center Network Engineering at Meta. That's what they've titled it. Now, if you look at the reason why I'm suggesting this paper is because when you consider Facebook, it's probably one of the perfect examples of an application that is driving the landscape of the modern applications. Right? It's one of the perfect examples of what modern applications look like. And because the Facebook application relies on a cloud computing infrastructure to support the application and the elastic demand of resources that a Facebook-like application has, It's a perfect cloud application to look at, to study. Okay? So in this paper, they've kind of introduced what is the Facebook cloud application traffic pattern. Okay? And it thereby helps you understand how the application traffic pattern is defining the needs from a data center network perspective. So as we said in the first introductory class on data center networks, I called it the application network dance, where I said the application leads, the network follows. But the two tango together to dance, right, as a pair. So this is a perfect example. Facebook application has its own kind of traffic pattern, which we read earlier. One of the paragraphs that we had taken out earlier from this case study said that while there is a ever growing north-south traffic because of new subscribers and new services coming in, it is still the tip of the iceberg, and the predominant traffic within the data center network is still they called it the machine to machine traffic, but we know it as the east west or server server traffic. So in this paper, they've actually tried to demonstrate the kind of performance limitations that Facebook encountered when they had to tackle the increasing machine to machine traffic. That's the term they will use, right? We are calling it east west traffic. When you are using more cluster driven design to supporting applications like the Facebook application. Okay, and then they talk about how they overcame this challenge by migrating to a fabric, to a networking fabric, which is an extension of the leaf spine topology used as the building block. Okay, so it's a perfect example of when I say leaf spine topology can be used as a building block to grow the topology to a large scale data center network. It is a perfect example of how they've used modularity in network design to design a building block that they call the fabric, and then using this fabric to create a larger scale of their network. Right? So in summary, when you look at their fabric, this is what it looks like. It's a typical leaf spine topology, but this is the building block fabric that they've used in creating the entire data center network. So what they have is 48 port switches. Okay, so we took an example with 4 port switches, if you remember last class, and I had talked about how can you scale the network if you had just 4 port switches. In Facebook data center network, the switches are actually 48 port switches, right? So they have 48 ports. They've created a building block with 4 fabric switches. They call it the fabric switches, term that we actually called as spine. Okay? And these are the leaf switches, which they also, and we also called as the top of rack switches. So because every fabric switch has 48 ports, in the building block that I have, I can have 48 top of rack switches. The criteria is still the same. Every top of rack should connect to every spine. So all the 48 ports on the fabric switches get utilized by connecting to the 48 top of rack switches. So the good thing about this diagram, it is in a colored way, it's showing you how the mesh connectivity looks like. Light purple, violet, green, and then the seal color, which shows demonstrate how the switches, Tor switches, are connected to the fabric switches. Now think of it like one plane. This is one plane, one block, one two-dimensional plane. And by the way, question to the class over here: how many servers can each top of rack now connect to? That's a question nobody is answering. Right? How many servers can each top of rack support? So 48 is the number of ports. That's correct, Aru. But 4 of the ports you see are getting utilized in connecting to the fabric switches. So yes, as Yuvraj said, 44 ports are still available on the top of rack switches. So I can connect 44 servers to each of these Tor, and therefore I can say that the maximum number of servers that each of these fabric planes can support is 44 into 48 total servers that can get supported. Yeah, right, Shubhraj. As part of one such fabric plane. Now, okay, anybody's done a quick calculation? How much does 44 into 48 translate to? I don't have a calculator in front of me, but somebody just do it. I mean, we just want to look at a number. Okay, so upwards of 2000. Thank you, Yuvraj. So 2000, yeah, upwards of 2000 is the number of servers that each plane can support. Now, what can I do if I have to go beyond 2000 servers? In the Facebook data center network, I can go for hierarchical configuration. That's what we learned. With the 4-port switches, we saw that you can create multiple levels of hierarchy. So what have they done is that, okay, let me blow it up a little, grow it so that it's clearly visible. Right, yeah. So now, okay, they've used the pod architecture. Remember, I had introduced two techniques. I said one is a virtual chassis technique and the other is a pod-based technique. So each of these fabrics that we showed on the upper way, this, they're calling this a pod. And what am I doing? Okay, look at it very, very carefully. I'm repeating pods. So each of these pods, as we said, has upwards of 2000 server connecting band space. And then I can have multiple such pods until pod Y is what they've said, right? And these they are calling as server pods, right? Because these are the pods which are connecting to the servers, right? So these are server pods. And what do you have in each of these pods? You have 4 fabric switches. So these are the fabric switches: 1, 2, 3, and 4. These 4 which I've highlighted are the fabric switches of what? These are the fabric switches of pod 1. Okay. Where are the fabric switches of pod 2? These are the ones. It may be a little difficult to initially read this diagram, but these are all fabric switches of pod 2. Now, what have I done? I have taken Y fabric switches and all 4, fabric switch 4, Y of them I've taken and put it into another plane, okay, where I have 48, now we called it super spine, 48 super spine switches, and these Y fabric switches are getting connected to the 48 super spines. Okay, that's how they are getting connected on the next plane. So this is the 3-dimensional structure that we had earlier talked about. Now, what does it give you? Okay, so this is the, okay, so they are, don't get confused with the terminology. They are using a different terminology. What we called as spine, they are calling fabric. What we called as super spine, they are calling it as spine, which is right. So these 4 planes that they've brought in, plane 1, plane 2, plane 3, plane 4, are actually the 4 planes connecting the 4 fabric switches. Okay? So this is what they're calling as the spine planes. And the spine planes are actually bringing in connectivity between the fabric switches of one pod to the equivalent fabric switch of the other pod. So pods 1's fabric switch 4 gets connected to the fabric switch 4 of pod 2 via plane 4. So plane 4 is connecting all the fabric switches number 4. Plane 1 is connecting all the fabric switches numbered 1. Okay? So this is how they are enabling 2000 into Y servers to be supported in a scalable architecture. That's what they've done. That's how they've created they've used a pod-based architecture to create a enormous size data center network. The capacity of the switches is also mentioned in this paper. There are high capacity 40 gigabits links connecting the fiber switches, the TOR switches, and the spine switches. So this is the kind of network capacity of each link that connects star to fabric, fabric to spine, 40 gigs. And within the rack, the servers connect to the top of rack switch via 10 gig links. Okay? That's the bandwidth that they've provisioned for data communication. So within the rack, if there's any communication happening between these servers, it's a 10 gig link, 10 gigabits per second link. But these are all 40 gigs. Right? So that's the cross-sectional bandwidth within the fabric. And then across this is also 40. All of these are 40 gig links. Right? That's how they've provisioned and created a huge scale data center network. Right? It's a use of the modular leaf-spine topology getting extended to 3 dimensions. So this is one paper that you may want to read, even though I've given you the gist of what it is. It is a good read if you have time and if you can spare time to uh, uh, talk about. Oh yeah, I forgot the edge. That's good, Yuvraj, you brought it up. Could you please talk about scalable uplinks, edge pods, edge switches? Do they play specific roles? Yeah. So, okay. So what are these edge pods? If you remember when we looked at the Google YouTube video, we had also, in an abstract sense, drawn it. They said this is the space where Google engineers sit and they work and control. So their workstations and cubicles are here. Then they have a networking room, and then they have a server room, and they also have a storage room. Right. So remember, the networking room was, they said, the room which enables the servers to connect to each other and for the servers to connect to the external world, the rest of the internet. So the edge pods are basically the ones which cater to the north-south traffic. They enable connectivity from this data center network to outside world. Okay, okay, I should not call it north-south only. It's basically outside the data center. So it is going towards the internet, but there's a lot of traffic. When we come later to the next classes, we will talk about multi-site data centers. Okay? So when there are multi-site data centers, let's say this is one data center, this is another data center, this is a third data center. These data centers are also connected amongst each other. Okay, multi-site data centers. So the edge pods are actually edge switches which are providing connectivity to the external world outside the data center. That's taking the traffic from the networking room to outside. So it could be traffic going over here to any other data center in a multi-site configuration, or it could be traffic going towards the internet. So that's what the edge pods are. Now, the reason why these edge pods may not be to the same number as what you see in the uh, inside of the data center network is actually representative of the fact that the north-south traffic, or the traffic that goes outside of the data center, is lower compared to the traffic that flows within the data center. The server is much higher. So 90% of the traffic, as we had talked about earlier, remains concentrated within this part of the network. But about 10% of it goes out from these edge pods and to the internet, towards the clients, or towards other data centers. So that's what the edge pods have been brought in for. Okay, they are scalable. Uplinks means connecting outside to the outside of the data center. Right, this is one case study, the data center, Facebook case study. Okay, another question on the window from Yuvraj. Spine, rack, and edge, all of them are exact same make configuration? Yes, that's correct. They are all of the same type. So they are built as commodity off the shelf switches. The next case study that you can read. Okay, one thing I missed talking about, which I'm introducing the case studies first, but this is what I intend to cover in today's class: the control plane of data center networks. Okay, when we talked about the internet, we said the networking layer of the internet has a very important role. The control plane in the network layer of the internet has a very important role, which is the role of routing. So how does traffic flow in a complex network like the internet? By using routing protocols. Same question holds true even in the data center network. We just saw it's a very complex network topology, three-tiered architecture with top of rack switches being kind of like your access switches, the fabric switches being like aggregation, and then the super spine, or they in Facebook architecture, the spine switches being like the core. The difference being the access aggregation core layers are all L3 connected. There's no L2 in this network. So they're all following a routing protocol. They're all using the IP networking. So what is the routing protocol that Facebook uses? I'm just introducing it right now. We'll talk more about it in today's class. They use BGP, Border Gateway Protocol. 4 demonstrates that they're using IPv4, so it's a BGP using IPv4, BGP4 routing protocol. So it's a distributed routing protocol, as we've already learned. It's path vector routing protocol. So BGP is why they are what they are using. Now the question that you may have is why BGP, why not OSPF? I'll answer these. Today's class, I'm going to cover all these topics. How should you pick a routing protocol for the data center network? But Facebook uses BGP, which is a distributed routing protocol. Remember, we also talked about the benefits of software-defined networking in a data center. Right? So what they've done is used a hybrid control plane. In general, they use BGP as a distributed routing protocol for identifying the routes, but they also have what they call as centralized BGP controller. It's like an SDN controller, which is used for centralized override. So they call this hybrid approach, Facebook calls this hybrid approach as distributed control centralized override. What does this mean? So I don't want in such a complex network everything to be done centrally with the software defined network. In general, I am letting the distributed routing protocol like it's used in the internet to work. BGP as a distributed routing protocol, I'm allowing it to work. And eventually, with, for every source to destination, BGP will enable finding a route. But sometimes I have special needs for some special type of traffic. That is where I can use SDN as an approach to centrally override BGP and override the routes that have been discovered by BGP with more centralized route configurations. So this is more like a hybrid approach, a mix of pure play SDN with pure play internet routing mixed together. They call it the hybrid approach, distributed control, centralized override. That's the term they've used. Okay. The next paper is about Google's data center. So Google data center network topologies have a nomenclature where they use the names of the planets to identify a generation of their data center network topology. Okay. So Saturn, Mars, that's the kind of names they've been using. So this paper talks about a network topology which is called Jupiter. Okay, so the paper is titled Jupiter Rising, a decade of clause topologies and centralized control in Google's data center network. So once again, the paper demonstrates how for a decade now, almost 10 years now, Google's been using the leaf spine topology in their data centers, clause, but the variant of clause called leaf spine. That is what they're using in their data centers. They talk about how Google data center networks run at, it's a multi-site data center network topology. So multi-site, you may not understand right now, it comes later in our course. But for now, just understand that it's multiple data centers connected together. It's what we are calling a multi-site. The Google data center network run at dozens of sites across the planet. It's like having 12 data centers connected via some networking methodology to create a multi-site data center network. And the capacity increase that Google has seen is over 100 times in the last 10 years. So the cross-sectional bandwidth that they've had to provision to handle this kind of server-server traffic is 1 petabyte bits per second, 1 Pbps bisection bandwidth. That's how high the volume is within the data center network, flowing between server to server. Okay. Now, they also in this paper talk about how they've designed their control plane for the data center network. And they say much of the general but complex decentralized network routing and management protocols supporting arbitrary deployment scenarios are overkill for single operator pre-planned data center network, right? So it's like saying you don't want a completely distributed routing protocol like the internet because it's an overkill. It's a single operator network, kind of another way of saying it's an autonomous system. It's under one operator control. It's an autonomous system. It's also a pre-planned data center network. It's not like every day the network topology is changing. It's a modular data center network like we saw with Facebook. It grows, it evolves, but it's not every day that the network changes. So it's a pre-planned data center network. And therefore, you don't need the complete complicated distributed network routing and management protocols as used in the internet. So what they've used is a more centralized control and management mechanism. This is what they've discussed in the paper. So this is where SDN fits in. Okay. Based on a global configuration that is pushed to all data centers. So this now we understand is our SDN architecture. You have a centralized control method. You calculate all the flow tables as based on a global configuration. You know the entire network topology. So you can do it at a central location. And then you push that topology to all the data center switches. Right? But because you also need to connect to outside, remember in the Facebook architecture also we had these edge switches. We have to connect to the outside world as well. So, oops, got stuck. Yeah. So what they've also done is they are still using BGP, standard BGP. Okay? But this is what they use between the border routers and the border routers talking to the external vendor gear. So if you think of the Google data center network as one autonomous system, internally within the autonomous system, they're using SDN, a centralized control. Okay? That's why the title centralized control is there. But when you have to talk to the rest of the internet, these are border routers like edge pods. They support BGP with the external vendor gears. Right? So this is how they talk using BGP to the external world, to the rest of the internet. Okay, internally, they're also using ECMP so that multipath routing can be utilized. Okay? Um, they also have a method, proprietary method for neighbor discovery. So in link state routing protocols, we saw that there is a method called link state advertisements, which is used to discover neighbors and their connectivity. Okay? Um, Google has defined its own proprietary, because it's an autonomous system, it can do anything within the network. They have their own proprietary neighbor discovery protocol that they've identified to detect the network faults, the liveness of the network. If any peer goes down, then detecting that. They have their own neighbor discovery protocol. So this is what they use for correcting cabling errors, which is a big challenge in large scale data centers. And in the section 6 of the paper, they've also talked about, in general, what are the data center challenges. Last class, I had summarized these. I said challenges exist in the case of congestion. So that is why you need bandwidth over subscription. Cooling is a challenge. Right? Cost is a challenge. So they've talked about challenges in congestion, fabric congestion, and why bandwidth over subscription is required. And how do you detect outages and correct those outages? Right? So that is where the proprietary neighborhood discovery protocol comes in. So while Facebook uses, as you saw, a hybrid control plane, distributed BGP protocol, but with a centralized override, Google uses a centralized control. predominantly. That's how their Jupyter network data center network is designed. Okay, so this case studies I just wanted to start off with by introducing, so you can, whenever you get time, if at all, you can read through it. They're good papers, actually, that give you good understanding of how practically large scale data center networks are designed. So back to our discussion where we left the last class. Um, so last class we were here. We were in our discussing the data center network technology evolution, and post L2MP, we said the NVO3 technology had come in. So the term NVO3, as we had just introduced last time, is network virtualization overlay. So the O over here denotes or brings in the concept of overlay network. So as soon as we talk about tunneling, okay, we are actually trying to create an overlay network over an underlay network. The underlay network, like in L2MP, the underlay network was Trill. That was the underlay network. But on top of Trill, I was connecting servers. So these were servers which thought they were connected over a L2 network. But the traffic between these servers was going over a Trill network. How? Using encapsulation, using tunneling. So I was taking the L2 packets of these servers, putting them into a Trill header, and then sending them over the Trill network by further encapsulating it into L2 packet, because Trill is like a L2++. It will further send it over L2 and over the physical layer to send it towards the remote side. So when you look at it like this, what is this network? This is an overlay network that you've created, a layer 2 overlay network over a Trill underlay network. Okay? In NVO3, we are doing slightly differently. Instead of this, we have an underlay data center network that uses the class topology and layer 3 networking. So it's a layer 3 class network, which is the underlay network. And on top, I don't care about the overlay. The overlay network, which is a tenant specific network being created between the tenant's server machine, that those could be L2, it could be an L2 network, it could be an L3 network, it could even be some other proprietary networking protocol that the tenant wants to use between its machines. So therefore, any traffic that gets generated by these server machines, S1, is treated as payload. It's encapsulated into a tunnel over the underlay network. It just flows as if it's payload for flowing through a layer 3 tunnel, like a VPN, similar to a VPN, and then reaches the other side where it is decapsulated and delivered to the other server machine, S2. So this is what we call as an overlay network. If the overlay network is completely, if you see in that sense, disjoint or independent of the underlay network. The overlay network can follow its own routing protocol. It can be built using L2. It could be an L2 network, an L3 network, a proprietary networking technology. But as soon as you use tunneling to carry its traffic over an underlay network, I can create an overlay network which is completely disjoint from the underlay network. Okay? So that's where the term NVO3 comes in. We are creating a virtualized network, NV, network virtualization, right? So this is the overlay is a virtualized network. It's network virtualization. O stands for overlay. So it's network virtualization, network virtualization overlay technology. Okay? So it's like a software defined logical network that you're building over an existing underlay network. Okay? It's completely decoupled from the underlay network, as we saw. It can run its own protocol. The lower underlay network doesn't care. For the underlay network, it's all payload. Okay? So what it allows you to do is to, when you can say that they're two decoupled networks, the overlay network is completely decoupled from the underlay network. Decoupled doesn't, they can evolve independently without impacting each other. They don't, the protocols are disjoint. They are not coupled together. So what it does facilitate is that the underlying clause network, the data center network, as we saw, is a scalable network. It's built for scale out architecture. So when I scale the underlying network, I can flexibly expand the underlay network. And that does not impact the overlay network at all because the two are decoupled. You can decide to implement SDN in one of these networks and not in the other or in both of them. It allows complete flexibility. So when you, let's say, introduce SDN based control in the overlay network, the SDN controller only needs to understand the overlay, the virtualized network topology. It is not required to understand or consider the underlay network architecture because the underlay will work on its own. It's like saying, if I have to create a path from S1 to S2, all the SDN controller needs to know is how should S2 forward the traffic. If it has to forward it to a network virtualization edge, that's the name we had used in NVO3 technology. That's what is the flow table it will configure. The NV knows how it has to forward it towards the remote entity. That's the underlay protocols coming into picture. Okay. So it facilitates two independent networks to coexist and decide on their own protocols how they want to work independent of each other. Underlay network can flexibly expand on its own. Overlay network can make its own choices with respect to how they want centralized control, distributed control without impacting the underlay network. So that's the beauty of using a tunneling and technology like this. So that's what we call as overlay networks getting created over underlay network, and in reality, tunneling enables all of them. So even NVO3 like L2MP is a tunnel encapsulation technology. This slide says layer 2, but in really it could be any. Right? We are still assuming like in L2MP that these servers are, sorry, layer 2, generating L2 packets. So in Trill, L2 packets were getting encapsulated in Trill. In NVO3 technology, L2 packets get encapsulated into IP, right, into a layer 3 protocol and then get transmitted over the class network. So it enables you to create, if these are L2 switches, it's like creating an L2 switched overlay network. Right? So it enables layer 2 communication between large scale VMs. S1 and S2 can be VMs. Okay. Essentially, what we are saying is this overlay network is in AWS terms a VPC, a virtual private cloud. S1 and S2 are VMs, VM1 and VM2. They could be provisioned on two different physical servers. But I can create a L2 VPC by using NVO3 tunneling technology. Yeah, Yuvraj, this question always comes and I always forget. There's something about three which every time my students ask me, and somebody in the group finds an answer and puts it on the chat window, but I always forget what that three was. I'll again request somebody to Google it. What does three mean in NVO3? And maybe post an answer. I'll also try to remember it for the next time my students ask that question. Okay, sorry, I don't remember that, Yuvraj, but somebody will answer. I think I've requested somebody can Google and answer. Okay, so NVO3 is a technology, is a technique or a technology, just like L2MP is, but like Trill is a protocol that follows L2MP technology. In the case of NVO3, VXLAN is the most popular protocol that uses the NVO3 technology. Okay, there are others as well. NVGRE is another protocol, network virtualization, generic routing encapsulation. That's what it's called, NVGRE. It's also popular, but predominantly VXLAN rules the space. It's a protocol that is used by majority of the enterprises. So in our course, we will only focus on VXLAN. If you want to study NVGRE, you're free to study, but we'll not cover it. Okay, so this slide, I generally just introduced it to help you understand that this L2MP, NVO3, the general fundamental behind these technologies is nothing new. It's not as if they brought in the concept of encapsulation or the use of tunneling first up. Tunnels have been used for time immemorial, even in the internet. right? So tunneling is only a encapsulation technique. It's a method to take a packet of any protocol and encapsulate it into a packet of another protocol in order to allow the first protocol to be carried over a network that supports the latter protocol. Okay? So what we're saying is you have this underlay network which supports protocol X, and I want to create an overlay network that supports networking protocol Y. It's completely possible because protocol Y will generate a packet which is compliant to the framing as per protocol Y. So it will create a frame. What can I do? When I pass it to underlay network, which supports protocol X, it doesn't even understand protocol Y. What will underlay network do? It will just treat all of this as payload, as data. Take that payload and encapsulate it in its own frame, putting its own headers for protocol X. And this is what we call encapsulation, because this was a packet in its own right with all its own headers and data, but it gets encapsulated into a lower layer protocol. And now the lower layer network can ignore this part. This is just data. It can look at these header fields and forward the traffic through it until it reaches the endpoint, where this header can get decapsulated and this payload packet can reach the destination. So tunnel, and we say that encapsulation has enabled me to carry a tunnel. Tunnel because everything passes through the tunnel unhindered, without being inspected, without being seen inside. So tunneling is a very old technology used in the internet, right? And we use it all the time. We use it. We've used it mostly when we use when we create virtual private network (VPNs). I sit at home, I connect my laptop over the internet. The internet is the underlay network. It's supporting protocol X, where X is equal to IP. X is equal to the IP protocol. That's what the internet follows. And it helps me connect to my enterprise network, where I can say that the enterprise network could be following a different protocol Y. Let's say Y is equal to IPX. It's a different networking protocol, IPX. So my laptop can be part of the private network and it can generate IPX packets. But as long as these IPX packets can be encapsulated into an IP packet, that packet can flow through the internet, reach my enterprise, where the IP packet will be decapsulated and the IPX packet will flow into the network. So it's like carrying an IPX packet over an IP network by creating a tunnel. And that's what VPNs are. They're tunnels created. Of course, VPNs go beyond. They also implement security. So the inner packet also gets encrypted. So it's not just that the inner packet is getting encapsulated, it's also getting encrypted. That's two things that we do in VPN, encapsulation and encryption, so that when the packet flows through the internet, nobody can even look at the content. And therefore, the enterprise traffic can flow from my home to the enterprise with confidentiality, without any loss of data, without any man in the middle attack or any leak of information. So it's like I've become a part of the private network by creating a tunnel through the internet connecting the two of us together. And that's why we call it a virtual private network. Okay? So nothing special so much about NVO3, L2MP, they're all tunneling technology. Okay. So in NVO3, we introduced this term last time, the network virtualization edge. This is the edge node which connects on one side to the overlay network and on the other side to the underlay network. It's the interworking entity. This is the one which creates the encapsulation, which does the encapsulation, and on the receiving side, the decapsulation. Okay. So before sending the frame to the destination endpoint, right, it will decapsulate the frame, and at the sending end, it encapsulates the data before sending it. So intermediate underlay network devices, they can just forward the encapsulated frame by looking at the outer header, outer encapsulation header. And the inner frame, nobody looks into it. For the network devices in the intermediate underlay network, the inner frame is completely oblivious. Nobody sees into it. Okay. Okay, let me diagrammatically show you. So this is the NVE. This is the NVE on the edge, on the edges. This is your class data center network. Okay, who's the sender? It could be one tenant virtual machine, VM1. Who's the receiver? It could be another tenant virtual machine, VM2. VM1 could be deployed on server 1, physical server 1. VM2 may be deployed on physical server 2. Server 1 and server 2 are connected how? Directly via the data center network, the underlay network. The VMs which are created on these servers are creating their own virtualized network. Right? So think of it like this: S1 and S2 are part of the underlay data center network. On S1, using virtualization technology, we've created VM1. On S2, we've created VM2. There can be other VMs as well. But these two VMs belong to the same tenant, and we are creating a virtualized network, which AWS terms we call it a VPC. And I want VM1 and VM2 to be connected together via an L2 network, let's say. So what is VM1 generating? An L2 frame with destination MAC address that of VM2. Right? It generates this L2 frame, destination MAC address VM2, NVE gets it, network virtualization edge gets it. What is this network virtualization edge? In the case of a VM, this will be a switch in the hypervisor. In general, and functions of NVE can be implemented in a physical switch or inside a hypervisor as part of the virtual switch. Okay? So when a VM is getting connected, a VM connects via a hypervisor. That's what we learned. So the hypervisor implements a virtual switch. The virtual switch functions as the NVE, network virtualization edge. It takes the frame, encapsulates it into an outer IP packet, and sends it to the data center network. The data center network will now route this traffic to the edge destination NVE as per its own routing protocol methods. Once it reaches the destination NVE, the destination NVE will decapsulate it and then give it to the VM. So the two VMs feel as if the L2 frame directly reached or got exchanged between them. And that's why we are calling it an overlay network having gotten created. But in reality, it was not a one-shot L2 frame routing from VM1 to VM2. It actually went over an underlay network. Anybody still have confusion about it, or is this very clear? By the way, nobody answered your question, Yuvraj, still. What is 3 in NVO3? You want me to Google it? I can do that, but I thought somebody will do it in the meanwhile. But question to the class, is this part very clear? You understand how encapsulation helps you carry a higher overlay networks traffic protocol? Yeah, okay, find it later. Yeah, let me also know. Post it on the chat. I'll try to remember. I'll also Google later on. Yeah, so it allows you to carry a overlay network pack frame following any protocol over an underlay network. Okay. So that's what NVO3 technology is. So as I said, in general, this concept of NVO3 can be used anywhere. The NVE function can be implemented in a physical traditional switch or a router, or in a virtualized network in a vSwitch inside of the hypervisor. Similarly, the endpoint that we saw in the diagram sending that data, it could be a virtual machine, as what actually happens in the case of cloud hosted tenant networks. But it could be a physical server, okay, where I want to create between physical servers like I do in VPNs. In VPNs, the laptop is a physical machine connecting to a physical machine in the enterprise network. So it's a physical machine. The endpoints acting as NVEs are on the laptop on one side and on the security gateway on the enterprise network side. So protocols, NVO3 technology can be used in virtual network in this whole cloud space. It can also be used in the internet in general, like creating a VPN. So VXLAN is, as I said, the most prominent protocol used in NVO3, following the NVO3 technology. It has a field in the packet header called the VNI, VXLAN Network Identifier. So just like VLAN had a VLAN ID, which was a 12-bit field, VNI is a larger sized field which gets encapsulated into the overlay header. And that is what I use to identify a virtual network. So this diagram that I had made on the next slide. Yeah. This is a virtual network. This virtual network has a VNID. VNID equal to, let's say, 5. So when I generate a frame from VM1, send it to the underlying network, the NVE, which does the encapsulation, in the VXLAN header, it will put VNID equal to 5. This is what identifies that the payload being carried in the underlay network belongs to a particular tenant's virtual network. Okay. So just like VLAN ID helped me identify a virtual network in layer 2 network in Ethernet networks using VLAN protocol, VNID helps me identify the tenant networks in a when I'm using VXLAN protocol. Okay, right. There was something I wanted to mention. I'm forgetting what was on my mind. Give me a minute. I had something I wanted to cover in this diagram. Yes, it came to my mind and then it slipped. I wanted to talk something about something came to my mind looking at this diagram. Let me read this. Maybe I'll remember what I. Okay, forget it. We'll get to it later. Some point I'll remember. We'll get to it. Okay, so this is in general what NVO3 is. Right, something on the chat. Could you please cover data flow between VMs created on exact same physical machine? How does it get routed? Yeah, I can. I will. In fact, that is something that comes in this course later. We will talk about VM networking, Yuvraj. Okay? Slightly later, maybe. Right? I am covering it in this course. So I will talk about later after we've gone through the general concepts of data center networks. I have a few classes where I talk about overlay networking. So right now we are still on the underlay network, the data center network, the DCN part. DCN is still the physical underlay network. Okay. When I come to overlay networking, I will talk about how VMs connect to each other, VM networking. I will even talk about how containers connect to each other. Container networking is also something I'll cover as part of overlay networking. We'll come to that topic. But in quick answer to your question is when VMs are created on the same physical server, this is the hardware of the physical server. This is the hypervisor. The hypervisor has a component called vSwitch. So the VMs connect via the vSwitch. So this route the traffic via the vSwitch. But I'll cover it later in a later class. When we come to VM networking, I will talk about it. Right now, my focus is more on the underlay network, data center networking. Okay. So yeah, I remember now what I wanted to cover. Sorry. So okay, forget it. It comes and then it goes. I don't know what's happening. So that's your question made me think of something, and then VMs. Let me read your question again. Data flow between VMs created on the same physical machine. How did it get routed? Came and went again. Yes, forget it. It'll come to me later. Something I thought was good to cover and talk about, but it's just slipping me. Right. So this slide we had covered last time. I'm skipping it. How do L2MP and NVO3 technologies stack up against each other? We said to large extent they are quite similar. They both are actually building overlay networks on top of an underlay network. The difference is that L2MP does it over an L2++ protocol like Trill, which requires you to invest into new hardware devices called the RBs, bring in new forwarding identifiers associated with those RBs, whereas NVO3 do away with all that need by saying, why not have an underlying L3 network? Why do I have to stick with L2? L2 was a concept I used when I was using access aggregation core topology. We are more and more moving towards IP technology as the perfect networking standard. So let's do away with all this L2MP stuff. Let's use IP on the underground underlay network. And then I can use IP identifiers. I don't need to create new hardware devices because IP routers will do the job. Okay? So basically what NVO3 is doing is they are removing the threshold to creating overlay networks on top of underlay networks, because I don't need any new infrastructure. I don't need new types of hardware chips or devices. And that is why NVO3 technologies, while they follow the same principles of L2MP, have become extremely popular. They can run with standard IP networks. Okay, so I will talk a little bit about VXLAN right now, so that I can enable the fourth lab activity for you after today's class. But more on the overlay networking, I will come to later. Okay? So I'll just introduce VXLAN because we are on the topic of NVO3, but then defer the rest of the discussion to later. So what is VXLAN? It's a protocol that follows the NVO3 technology, and it enables forwarding any higher layer frames. Wherever you read L2, it can actually also be L3, or it could be actually any proprietary overlay protocol. It doesn't matter. But because we are coming from a history where access aggregation core servers were connected using layer 2 technology, we are still saying servers are L2 servers and we are connecting them over an underlay network. We're saying VXLAN also allows you to do that. You can take L2 frames from servers and carry them over a underlay data center network, which actually uses layer 3 IP technology. The encapsulation method that they follow in VXLAN is not direct encapsulation into IP. It's actually called a L2 over L4, or sometimes also called MAC in UDP encapsulation. Okay, so it's not that I'm taking the L2 frame of the overlay servers, this is overlay, and directly encapsulating it into a L3 IP packet. No. Actually, what VXLAN does, and I'll answer later why it does so, is instead of directly encapsulating it into an L4-3, it takes the L2 frame, treats it like payload, and first puts it into a L4. Puts a L4 header. It treats it as if it's application payload coming to transport layer. Puts it in an L4 header, which then goes through L3, which is IP, and then goes to L2, and then over the physical link L1. So this encapsulation which VXLAN protocol uses is called L2 over L4, or MAC. This is the MAC frame that the server has generated. MAC in UDP. L4 is UDP. So they are using UDP protocol instead of TCP. MAC in UDP encapsulation is what VXLAN proposes. We'll see why. Why do they don't directly encapsulate over L3? Why do they use UDP in between? I'll answer that later. So it uses MAC and UDP encapsulation. The VXLAN protocol is also standardized by the IETF. And it's, as we said, allows you to create an overlay network between VMs. VMs can get migrated from one physical server to another physical server in the data center, and yet it can remain connected within the overlay network to other VMs. Okay? So it's kind of an isolated, independent, decoupled VPC in its own right. Okay? That's what it does. So this is how you visualize the VXLAN protocol running in the cloud network. So this is your data center network, or the underlay network. It's an IP network, as we said. It follows the class topology. It's an IP network. Yeah, and Jyoti, I'll come to what is the UDP port used by VXLAN. So the source and the destination are used differently. I'll answer that question slightly later, 3 slides more later down the line. Okay, so this is your underlay network. And what am I creating? I'm creating multiple virtual networks on top. Let's say, yeah, so you see these VNIDs, VNID 5000 is one virtual network. This is one overlay network. Let's call it VNI 5000. That's what we've called it. Virtual Network Identifier 5000. 2 VMs are a part of it. Similarly, this is another virtual network that's been created as an overlay network on top of the data center network, underlay network. It's identified by VXLAN network identifier 7000. Okay? So as you can see, these VMs are spawned using server virtualization. I have a hypervisor sitting on that server, which supports multiple VMs. But 2 VMs on 2 different physical servers can be part of the same overlay network. This is what we expect. So how do I send the traffic if this VM belonging to virtual network 5000 wants to send traffic to another VM, also part of the same virtual network? How would it do? It will generate a L2 frame, give it to the NVE, Network Virtualization Edge. The Network Virtualization Edge in VXLAN protocol is called VTEP, VXLAN Tunneling Endpoint. Okay, so NVO3 technology, we use the term NVE. VXLAN is a protocol following NVO3. So in a VXLAN protocol, the term NVE is replaced by VTEP. V stands for VXLAN, T stands for tunneling. So you're creating a tunnel. EP is endpoint. So it's a VXLAN tunneling endpoint. It will take your frame and tunnel it towards the destination. Oh, now I remember what I wanted to tell you. Yeah. So the point I wanted to make in the previous slide, I continued to forget is, one question which nobody has asked me on the chat yet is, how does this VTEP know that when the traffic, okay, let me rephrase it. So this server has generated a L2 frame. Okay? What is the destination MAC address in the L2 frame? Destination MAC address is actually the MAC address of this VM. Let's call it VM2 is equal to the MAC address of VM2. What is the source MAC address? Source MAC address is the MAC address of VM1. We are calling this VM1. Okay. Now, as soon as this frame reaches VTEP1, how does VTEP1 know that the tunnel has to be created towards VTEP2? Okay. Or in other words, the question is, how does VTEP1 know that VTEP2 is the device handling VM2? How does it know that? So they can many VTEPs in this data center network. How does the source VTEP knows which is the destination VTEP? There is nothing in the MAC address. In fact, we said VMs can even get migrated. Right now it's running on server 1. Tomorrow this VM might get moved to another physical server. And that different physical server may be supported by a different VTEP. So how does VTEP1 know that it has to create a tunnel with VTEP2? Keep that question in your mind. That is what we are going to answer in the later part of today's class, if time permits, but otherwise the next class. Okay, remember this question. So far we've said the NVO3 protocol and similarly the L2MP protocol works because somehow these encapsulating endpoints know where to create the tunnel to. But how do they know that? How do they know which VM is serviced by which VTEP? That we still not said. So I'll come to that part of the question in today's or maybe next class, but keep this question in your mind. That was what was on my mind and I was forgetting. But assuming that somehow VTEP1 knows that VTEP2 is supporting VM2, it will create a tunnel. The traffic, this frame will get tunneled through the network to VTEP2. VTEP2 will decapsulate it, give it to VM. And this is where the tunneling comes in. It's MAC and UDP tunneling. Okay. So the benefits of using VXLAN is that one, of course, it helps you create those tenant-specific networks or overlay networks. But the bigger benefit is it's highly scalable. Instead of using a 12-bit VLAN ID, it actually uses a 24-bit segment ID, which we have called the VXLAN network ID or VNID. Okay. So, okay, Arup is already guessing that it is table being used to know. We'll come to it. Yeah. So table is one of the methods. Routing is another method. I'll talk about both techniques. When we'll come to VXLAN control plane, we'll talk about how this is discovered. Right. So VXLAN has a 24-bit ID called the VNID. And this VNID being 24-bit, it enables 2 raised to power 24 or more than 16 million virtual networks to coexist in the same administrative domain. So with the same data center network, where VLAN ID could only support 4,000 tenant networks, VXLAN can support 16 million networks. Okay. So it basically does away with the limitation that VLAN had. And because it runs using the NVO3 technology over an underlying layer 3 network, it can take complete advantage of layer 3 routing coupled with ECMP routing to overcome the limitations that we saw earlier with VLAN being used in access aggregation core network, where the STP challenge was coming in. Right? So it does away with all those problems. Okay, Yuvraj says we are using tunnel word here. Does it mean that this tunnel lives for longer period of time till the data is transferred from one edge device to another? No. It doesn't mean the tunnel exists for a very long period of time. Tunnel is just, think of it like an encapsulation. It's a word being used for encapsulation. Okay, that's all. As many packets come in the data plane which need to be sent to the other side, I'll encapsulate them and send. When the packets are no longer coming, there is no encapsulation happening. It's like the tunnel is no longer existing. So there's no explicit setup of the tunnel or deletion of the tunnel. In fact, tunnel is an abstract term here. Encapsulation is a real thing that is happening. It's giving you a feel as if packets are flowing through a tunnel. But there's no real tunnel. There's no real tunnel getting established via control plane protocol or getting deleted. Nothing like that. As long as encapsulation exists, the tunnel is existing. Okay, so this is what VXLAN is. Now we will look at the UDP encapsulation, MAC and UDP encapsulation. What is happening? Oh, I completely missed. We are well past the 1 hour boundary. You people need a 5-minute break before I go ahead with what is VXLAN, how does tunneling, encapsulation work, MAC and UDP. I think we are already 1 hour, 14 minutes into the class. Yeah, you need a break. Okay. So take a 5-minute break, 11:44 by my watch. 11:49 I will start. So come back in 5 minutes. Okay, uh, back up a break. So I just quickly checked Google what NVO33 stands for. So it's layer 3. Yeah, so you were right, Vijay. Yuvraj, sorry. It does stand for layer 3. So it says network virtualization over layer 3. That's what it is. Okay. Yeah, so let's look at VXLAN encapsulation, the packet format. So as we said, the transport protocol used with VXLAN in the data center underlay network is UDP-IP. So that's what they use. IP, we know it's an IP-based network. The UDP is the layer 4 transport layer protocol used with VXLAN. So in the MAC and UDP encapsulation, VXLAN will basically tunnel the higher overlay network layer 2 packets over the underlay layer 3 network by first encapsulating it into UDP and then sending it over IP. So this is the original L2 frame, if you look at it. This is what the VM has generated. VM1 has generated it to be sent to VM2. It's the original L2 frame. So VXLAN will first put a VXLAN header. Why do I need the VXLAN header? Because this is where I have the VNID. This is where I am able to distinguish between the different tenant network. Okay, so this you can see is the VXLAN header. This. So you have some 8 bits of reserved field, which is kept for later. You have this 24 bits VNID. This is what gives you 4 million tenant networks, virtual networks. And another 8 bits of reserved field for later, reserved for future, for some other use that may come in. And some flags which are used by the VXLAN protocol. We'll talk later about what these flags are. So these are 8 bits of VXLAN flag. So this is 8 byte of header that I first put on top of the original overlay network L2 frame. Once I put this VXLAN header, now this thing that I have, see over here, this is what I see it or treat it as an application payload. Think of it like an application layer message. And I pass it to the UDP protocol. So UDP will put in its own header. We've seen the UDP header now. So what does UDP have? It has its own checksum. It has the UDP length. It has a UDP source port, and it has a UDP destination port. So what is the UDP destination port? Because the destination is actually the VXLAN protocol. The UDP destination port is actually the port defined by the VXLAN protocol. Okay, so this is the first answer to first part of your question, Jyoti. The destination port number used in the UDP header has a fixed value of 4789, indicating that when this packet reaches the destination, okay, I'll erase all that I've drawn here. When this packet, L2 packet, reaches this point, the destination, the UDP layer knows by looking at destination port 4789 that this packet is to be given to the VXLAN protocol. It's meant for the VXLAN protocol. Okay? So that is the destination port number fixed to 4789 to indicate that it is to be given. The UDP packet has to be decapsulated and given to the VXLAN protocol. So think of VXLAN like an application layer sitting on top of UDP. Okay, it's like an application sitting on top of UDP, and it has its own destination port number 4789. Now, the source port number on the other hand, it's not fixed. Okay? The source port number, the sending VTEP, puts a UDP source port number, and this source port number by the standard is defined to be the hash value of the original L2 frame. What does that mean? Everybody understands, by the way, what hash functions are? Yes, no? What is a hash function? It's a mathematical function that we use a lot. Even in cryptography, we use it a lot. Anybody who doesn't, I want to see a no if, because otherwise I'll not explain what a hash function is. If I say yes, I believe a lot of you will say yes, but anybody who says no, I can explain it. Arup, what is DHT? I don't know that. For discrete something, I don't know. I'm guessing DHT. What you meant by? Okay. Anyway, a hash function is just for quick. A hash function is something that can take a variable size text and give a fixed size output, okay, and follow some properties. The properties are if x is not equal to y, where x and y are these inputs to the hash function, then h of x will never be equal to h of y. It's basically saying that if you give the hash function two different variable inputs, it will generate two different hash values. That's what is important here. It also has another property which is more used in cryptographic algorithms, which is that it's a one-way function. If I give you x and the hash function, you can generate h of x. But if I give you h of x and I give you the hash function h, you cannot get back to x. It's a one-way function. Yeah, that's a property used in cryptography. But for now, just remember hash function is a function such that given a variable length payload, it will generate a fixed size value, we call it the hash value, such that if the input x is not equal to input y, then the hash x will never be equal to hash y. That's the property of hash functions. Okay, so what is VXLAN saying? VXLAN is saying take the original L2 frame. It can be a variable length frame. Pass it to a hash function as the input. So this is the L2 frame. What we will get is a fixed size hash value. Right? You have a 16-bit hash value. That value is the source port. Okay. So because the L2 frame will all be different, and because of this property of the hash value, we know that the source port will keep on changing. Why do we need this? The reason why the protocol has defined the source port to be such is because in data center networks, as I said earlier, we use, in addition to the standard routing protocol, the ECMP protocol, equal cost multipath routing protocol. Okay? And ECMP is defined in such a manner that when there are multiple parallel paths equal cost between a source and a destination, let's say these are multiple equal cost paths that exist between a source and a destination. How does ECMP distribute the traffic across multiple paths? It uses the UDP port numbers. Okay, so if there's the same traffic going from source S to destination D, it will use the UDP port numbers to send the traffic or distribute the traffic across multiple equal cost paths. So it's like looking at the source application and the destination application, looking at application level traffic flows. And for different applications, the traffic flow is getting distributed on different equal cost paths between S and D. Okay? Now, VXLAN uses this trick to make sure that the traffic from VM1 to VM2 is actually able to make use of the underlying data center network bandwidth by getting the traffic between VM1 and VM2 distributed over multiple equal cost paths. Right? So this is a trick that VXLAN uses. It basically uses the source port as the hash value of the original Ethernet frame so that this port value keeps on changing. And therefore, ECMP in the underlay network will see these differing UDP ports and send the traffic over the multiple equal cost paths. It will distribute the traffic across multiple equal cost paths, thereby better utilizing the underlay network value. Okay, that's how the UDP port number is chosen. I think now I've answered completely your question, Jyoti. Okay, what is the UDP value for VXLAN? So the destination port number is fixed as 4789. The source port number is a hash of the original L2 frame. Right. So now that I've encapsulated it into a UDP header, what is the next step? UDP is layer 4 protocol. So next step is layer 3, next step is layer 2, and then it goes over the physical wire. So the next will be an IP packet, IP header that will be put in. And lastly, there'll be an Ethernet header that will be put in. If you remember, the Ethernet header also has a VLAN ID, but I don't need to use the VLAN ID in the Ethernet header because I'm actually using the VNI to distinguish between virtual networks. So actually, it don't need to use VLAN ID. So I can use a normal non-VLAN Ethernet header. I don't need VLANs underneath. Yuvraj, how variable source port number helps ECMP wasn't very clear. Could you please repeat? No, I did not explain ECMP because we haven't studied ECMP. I just noted that ECMP, see, what is the port number? When we studied UDP, what did we say? What is the port number distinguishing? Port number is distinguished in between applications, higher layer applications. So one application has one port number, the other has another UDP port, and so on. So ECMP actually works in such a fashion that if there is traffic being generated from different applications, but from the same source, it will send that application traffic over different paths. And for that, it uses the port number, source port number. So VXLAN just played around with it. It forced the port numbers to keep on changing from one VM to the other so that the traffic between the same VMs actually ends up going over multiple parallel paths in the underlay network. That's all I explained. We didn't go into ECMP and why ECMP does this, but this is how ECMP is designed. It looks at UDP port numbers to send the traffic over different equal cost paths. I mean, there has to be a way to load balance through the network. Right? ECMP uses the UDP port numbers to load balance equal cost paths. Okay, so we put a IP header. We also put a Ethernet frame. So what will be the source and destination addresses in the IP header and the MAC header? The source IP address and the source MAC address will be what? It will be the IP address and the MAC address of the source VTEP. Is this clear? VTEP is doing the encapsulation. Right? So when it takes the original L2 frame, first puts it into a VLAN header, then puts a UDP header, then puts a IP header, then puts a MAC header. The source IP address in the outer IP header and the source MAC address in the outer MAC header will be the IP address and MAC header of the VTEP, source VTEP. Right? The VTEP where the source VM belongs. This should be clear. What is the destination IP address? The destination IP address is the IP address of the VTEP where the destination VM belongs. This should also be clear. The only part that may not be clear is how does the source VTEP know the destination VTEP handling that destination VM? And that question I said, remember, we've parked it for now. We will answer it at a later time, maybe in the next class. I don't look like we'll reach that point today. So the only thing we've not answered yet is how does the source VTEP, looking at the destination VM, get to know the destination VTEP? So that's the only thing we've not answered. But assuming that it has some way to get to know which is the destination VTEP handling the destination VM, The destination IP address in this outer IP header will be that of the destination VTEP. That's the IP address. Now the trick question to the class. What is the destination MAC address in the outer MAC header? If you remember your networking fundamentals that we learned in the initial part of the course, what is the destination MAC address? The destination MAC address is never the MAC address of the destination VTEP. It will be the MAC address of the next hop device on the path to the destination VTEP. So this IP packet will get routed through the data center network so that it can reach the destination VTEP IP address. But in between, it will pass through routers, multiple routers. What did we talk about routing? Routing is a hop by hop routing approach. The source VTEP knows what is the next hop router R1 to when going to the destination. R1 knows the next hop is R2. R2 knows the next hop is the destination VTEP itself. So when S creates the MAC address to reach D IP address, what is the outgoing MAC address? It puts the MAC address as R1. So R1 will get the packet, it will decapsulate L1, look at the IP packet, look at the destination IP address as D, look at its route table, and then forward it to R2. When it forwards it to R2, what does it do? It puts the MAC address of R2. So what is the outer MAC header carrying in the destination MAC? The destination MAC is always the MAC address of the next hop device. Hop by hop routing. This is what we learned during our network fundamentals, right? So this is what your VXLAN packet format will look like. So now you know why I used UDP in MAC encapsulation. Oh, sorry, MAC and UDP encapsulation. I brought in UDP because I wanted to make use of the benefit of ECMP under it. Right. If I would have directly taken the L2 network packet, this original frame, put it in VXLAN header, and then if I would have avoided UDP, I could have done that. I could have taken the VXLAN header and directly put it in an outer IP packet. But then I would not have gotten the benefits of ECMP. You see that? Right? Because I take the L2 frame, I put it in VXLAN header, and I put it directly over outer IP. This like becomes your what we call as the raw transport layer. It's like taking the application layer payload and bypassing the transport layer. The transport layer is here. I bypass the transport layer and directly give it to the IP layer. This is, by the way, in networking terminology called a raw socket. I don't want to use either TCP or UDP. It's called a raw socket. So when I don't use TCP or UDP, ECMP will not be able to benefit out of it. And hence, in order for me to use network load balancing, underlay data center network, because of the clause topology, we said clause topology enables what? Multiple equal cost paths between the same pair of servers. And because I want to use all those parallel equal cost paths to make better use of the higher bandwidth available in the network, I'm doing all of this. I'm defining VXLAN to follow a MAC in UDP encapsulation, not a MAC in IP encapsulation. So that when I do MAC in UDP encapsulation and I set the UDP port numbers like we just explained, I can better utilize the benefits of ECMP in the underlay data center network. Make sense? So this is what VXLAN does. MAC in UDP encapsulation. Okay. By the way, for all practical purposes, this could have been an original L3 frame. I don't care. The encapsulation would have been the same. Okay. So if the two VMs want to have a virtual private network created between them, which they see as a layer 3 network, that's fine. They will generate IP packets to send from VM1 to VM2. VXLAN can do that. It has to function the same way. It will take the VM traffic, which is a L3 frame now, encapsulate it in VXLAN header, then UDP, then IP, and then MAC and send it. So while we call it a MAC in UDP encapsulation, this is because of historical reasons, right? When we come from access aggregation core, the servers were always L2 connected over a L2 network, layer 2 network. And therefore, VXLAN also supports layer 2 overlay networks over a underlay layer 3 network. But actually, I can support a layer 3 overlay network over a layer 3 underlay network also. And as I said, for all I care, this could even be a proprietary networking protocol. I don't care. For me, it's only a payload. Right? So I can support any form of overlay network over the data center network using the VXLAN. That's what we've learned. That's the important lesson from today's class. The VXLAN provides me, and that's why on that earlier slide where I talked about overlay NVO3, I said the overlay network is completely decoupled from the underlay network. Right? I'm not even peeking into the original frame. I don't want to peek into the original frame. I want to keep the two network completely decoupled. Right? Okay. So this diagram is just showing you that VXLAN can be used even in physical networks. Right? It's not just, we've talked about more in the cloud computing sense, where VMs are trying to send traffic to another VM over a virtual network. In reality, you can even have physical network like VPNs. So this could be your enterprise network. Or let me say, okay, this is your head office of your enterprise. This is your branch office. And this is your internet. So the branch office and the head office are both connected via the internet. The branch office has its own local LAN. The head office has its own local LAN. When end systems within the branch office want to talk to each other, they talk via the local LAN. Similarly, when end systems on the head office want to talk amongst each other, they communicate over the local LAN. But what if an end system X in the branch office wants to talk to an end system Y in the head office? I can use the VXLAN protocol. Yes, I can bring in a VTEP in the branch office. I can have a VTEP in the head office. X will send a frame to the VTEP. VTEP will encapsulate it and send it over the internet, just like we were sending it over the data center network. It will reach the destination VTEP, and that destination VTEP will then decapsulate it and send it to the end system. So VXLAN is a very generic protocol. NVO, and in that sense, NVO3 is a very generic technology. And that is why that earlier statement that I had on one of these slides where I had said, yeah, this slide, that the NVE could be a physical switch or a virtual switch in the hypervisor. The sender, it can be a physical server or it could be a VM. VXLAN can work either ways, or NVO3 technology doesn't care. Okay? So in this diagram, you're actually seeing physical servers and physical networks getting connected via a transport IP network. Now, take this diagram, replace this end system with a VM, VM1, this end system with as VM2, this end system as VM3, and this end system as VM4. Okay, this local LAN segment is nothing but the LAN segment that is now within the hypervisor. So the hypervisor has a vSwitch. I'm trying to partly answer the question which was asked to me earlier, VM networking. How do VMs within the same physical device? And think of this as physical server 1 and this is physical server 2. And these physical servers are connected over the data center network. So all I've done is I've changed, given them different names. But VXLAN works the same way. When VM1 now wants to talk to VM2, just like earlier it was communicating over the LAN segment, now it's connected via the vSwitch. The vSwitch in the hypervisor helps connect the two VMs together within the same physical server. Similarly, VM3 can talk to VM4 using a vSwitch, virtual switch. that exists within the hypervisor. But when VM1 wants to send traffic to VM3, the V switch in the hypervisor also acts like the VTEP. Okay, so VM1 sends a frame with destination VM3. The V switch in the hypervisor, which also acts as a VTEP, will do the VXLAN encapsulation function and send it over the underlay data center network. The data center network will naturally route the traffic towards the destination VTEP. The destination VTEP will decapsulate it. That destination VTEP will be the V switch in the destination hypervisor. It will decapsulate it and give it to VM. So VXLAN protocol works with a VTEP being a physical server or a VTEP being a physical switch or a VTEP being a V switch, virtual switch. With a sending node being an end system physical server or a sending node being a virtual machine. Doesn't matter. It's a generic protocol that you can use to connect branch offices to head offices over the internet. And it's a protocol that you can use to connect tenant-specific VMs to each other over an underlay data center network. The same protocol works. Right? So with this, I'm saying there are two parts in the control plane that we now need to talk to. If you've so far understood the things, right, then what are the two parts that we've talked about? We've talked about two things. One, the source VTEP creating a packet for the destination VTEP and that getting routed via the data center network. Right? So one part of the control plane is the control plane of the data center network. How does the routing function get implemented in the data center network? Something which we were studying in the Google and Facebook case studies. Facebook said, I use centralized control. I use distributed control with centralized override. Google said, I use centralized control. They were talking about the routing mechanisms in the underlay data center network, which allows them one VTEP to send traffic to another VTEP. How does this routing work? This is what we are going to talk about and start talking about today. I'm calling it the control plane of the underlay network, the data center network. But then there's another part, the question which we had parked earlier. And the question which we had parked was, how does a VTEP in the overlay network know what is the VTEP serving the destination VM? So this is the source VM, this is the destination VM. How does source VTEP get to know which is the destination VTEP serving it? That is the control plane that exists in the overlay network. And that is what we are calling as the control plane, because the protocol that we are using is VXLAN, control plane of the VXLAN protocol. How does that help us discover the VTEP serving the different VMs? That's the control plane of the VXLAN protocol in the overlay network. So here we will talk about how routing happens in the overlay networks. How is this discovery done? Which VM is being serviced by which VTEP? That's the control plane in the overlay network. So I'll first talk about routing in the underlay network. Then I will talk about the control plane over the overlay network, and both these questions will get answered. Right. Let me look at the chat for a moment. Why UDP and not TCP protocol is used here? See, I don't need reliability in the underlay network. That is something I will let the overlay networks decide. I can't, in the underlay network, I cannot make a decision for the overlay network. The overlay networks may be running real-time protocols, in which case TCP doesn't work. So if TCP is required, TCP will run, but TCP will run in the virtual network. So you see this original L2 frame. TCP will be somewhere within this. If I blow up this original L2 frame, it will be L2 header, followed by L3 header, followed by TCP header if TCP is required, and then the application payload. So if the tenant network requires reliability, the TCP will already be there in this original L2 frame. I don't need a double overhead of TCP. Yeah, I think you answered your question yourself. I did not read the remaining part of your question. Since network is managed under same AS, the additional TCP overhead will end up being an overkill. It will, yes. Right? I don't need two levels of TCP. And I can't even make the decisions for applications running in the tenant network. So I'm just using plain UDP only to enable ECMP to do its job. Okay, reliability if required in the tenant specific virtual network is the responsibility of the tenant. Let the tenant decide whether it's supposed to run its applications over TCP or it's supposed to run its applications over UDP. Let the tenant make that decision. The underlay network, the VTEP will just packet it into UDP and send it. Yeah, so Arup, you got your answer. The vSwitch is always there when we have a VM. That's right. Right? Only when it becomes a VTEP when we use VLAN. That's correct. Yes. So every hypervisor has a vSwitch, and vSwitch in the hypervisor enables VMs to talk to each other. But when you want VMs across physical machines to talk to each other, you need VXLAN, and that is when the vSwitch additionally functions as a VTEP and uses the VXLAN protocol to connect VMs across physical servers. And that is how tenant networks, virtual tenant networks are created in a cloud environment like the AWS. So this is how where you will be able to link between what you're studying in cloud computing course to what you're studying here. In cloud computing, your instructor would have told you, use the AWS console to create a VPC, spawn VMs, connect the VMs using a vRouter. He's teaching you how to create a VPC, but actually how are these VMs, which may be getting spawned over different physical servers, really able to send traffic between themselves using VXLAN protocol, with the vSwitches acting as VTEPs. So this course actually complements the cloud computing course to help you understand beneath the scenes, how are things working? How is the VPC getting working in a cloud environment? This is what helps you understand. Okay, that is why this is a core course for you to do. Helps you get the basic understanding of how cloud computing functions. How am I able to create these tenant specific networks in a data center network or a data center? Right. So, okay. So this is what VXLAN is. Right. I think I'll just conclude VXLAN today and stop the control planes that I talked about, the DCN routing protocols and the control plane of VXLAN. I think we'll do next time. These are bigger topics. We'll conclude VXLAN topic and close today's class. Okay, one more question from Yuvraj. General question, number of acronyms are increasing further with each NFC session. Is there a way to remember them to avoid getting them confused between each other? Yeah, maybe it's a challenge initially for me because I've been seeing them for a long time. Maybe it all sounds very, very easy to remember because they all have a very logical expansion. VNI, virtual network identifier, VXLAN, virtual extended LAN, local area network, NVO3 network. But don't worry so much about abbreviations, I would say, Yuvraj. Even if you remember what is NVO3 and you don't know the full form of NVO3, anyway, I'm not going to ask you in the exams, define what is full form of NVO3, or I'm not going to ask you what is the full form of L2MT. Maybe I don't even remember. Yeah, I do remember layer 2 multipathing, but I don't expect you to remember. Yeah, so not that way, but you're worried about the acronyms. Don't worry about acronyms and worry about more if you understand what is the concept behind those terms. Right? So when you see L2 MP, you should remember it's a L2 technology. NVO3, it's a layer 3 technology to create overlay networks. That's probably the easiest way. 2 L2, 2 in the L2, 3 in the NVO3. That's what helps you remember. So once you go a few times through these slides, actually there are not too many abbreviations is what I feel. Okay. Anyway, so VNI, as we've already mentioned, it's a identifier in the VXLAN header that identifies the tenant virtual network. In the overlay part, it identifies an overlay network over the underlay network. It's a 24-bit field value. Valid values as per the specification are from 4096 to 16777.215. Now, I'm not sure what is the reason for not starting from zero. I'm just guessing that they wanted to avoid the overlap with VLAN ID. Okay, so 0 to 4095 are the IDs used for VLAN ID to identify tenant specific network using VLAN IDs. So they avoided by saying, okay, we can continue to use 0 to 4095 as the virtual networks that can get identified using VLAN ID. And beyond 4095, from 4096 to 16 million plus, these are the networks which we will identify using VNID in the VXLAN header. So if you remember that diagram I showed you, there are both. When you do this encapsulation, there's also VNID and there's also a VLAN ID that I can make use of. So I'm just guessing that maybe this is what they said could be used for virtual networks 0 to 4095, and this is what I can use for virtual networks 4096 onwards up to 16 million. Right? So they might have said, okay, VXLAN ID stands, valid value starts from here, 4096. Just for completeness, I'm telling you that VNIDs can be scoped in two fashion. One is a network-wide scoped VNI and the other is a logically assigned VNIs. Okay? What we've so far been talking about is network-wide scoped VNI. Basically, it means the VNI value is unique across the entire data center network. So VNI 4000 is a unique VNI across the data center. It identifies a virtual network across the data center. Okay? 4000, 5000 denotes a different. It's a network scoped. It's basically saying the uniqueness of the ID spreads across the underlay network. Okay? So generally we use network scoped VNIs because it's easy to do that. We are saying the same ID is used, understood across the network to identify a unique virtual tenants network, virtual network. But there is also a concept of locally assigned VNIs, which uses the semantics of a general switching network. In switching, what happens? A circuit switch network. In an MPLS network, in ATM switch networks, generally what you do is you have locally switched identifiers. So you say, I use an identifier VNI equal to 1 to denote a virtual network on one interface. But on the next link, I can switch the value to VNI 4. It's denoting the same tenant specific virtual network. Okay? But the same tenant specific network is known as VNI 1 to this node, VNI 4 to this node, and so on. So I keep switching the ID value across each node to node. So it's basically saying the VNI has local significance only. But I don't want actually to get into this a lot and maybe confuse you. So you can just, if you don't understand this, if you don't understand how MPLS works or how the local significance works in a switching protocol, then just ignore this part. It's not too important. Right. So yes, Yuvraj, your question is a future question. How about tenant networks and across multiple data centers? Would they have the same VNI? I mean, it's a relevant question at this point because I'm talking about network scoped VNIs. So this is one place, Yuvraj, where locally assigned VNIs can come in handy. I can use one VNI value within one data center and then switch to a different VNI value across a different data center. So yes, you are right. You can think of this as one data center, this as another data center, and it's actually and the overlay network is actually spanning across data centers. So this use case, by the way, I'll talk to when I come up to multi-site data center. This is one of the use cases of multi-site data center. The same overlay network can spawn across 2 data centers. And there you might find use of locally assigned VNIs. One data center has VNI 4, the other has VNI 1. So actually in the intersection point, I'm switching VNI. So you can call it a locally assigned VNI. The scope of the VNI is limited to one particular network edge or one particular data center. But as soon as the traffic enters another data center network or another edge of the network, the VNI ID changes, even though it's denoting the same tenant virtual network. Okay, so VXLAN does allow both types of scopings of the VNID. It's like saying, what is this? When you do programming, you say the scope of my global variable is across the entire file, but the scope of my local variable within a function is only the function itself. It's something similar to that. Okay, so it's basically the scope of the VNI. Okay, I think this should be the last slide. Yeah, last slide for today. Okay, anyway, time is out. I'm just quickly covering it. It's just some definitions, which if you remember, good. If you don't, no worries. I'm not going to use these definitions or ask you anything. But just from a completeness standpoint, I said VTEPs could be physical switches, VTEPs could be V switches. Right? And in a cloud computing environment, there could be some VTEPs on physical switches and some VTEPs on V switches as well. So this is just terminology followed in the specification. When you create an overlay network, this overlay network that I showed you, where the VTEPs were all on physical switches. I had a branch office connected to a head office via the internet. This kind of a overlay network is called a network overlay. Network overlay means all VTEPs are deployed on physical switches. It's a terminology that's followed. If you don't remember this terminology, don't worry. I am giving it to you for completeness of the protocol. But if you don't remember, there is no worry on it. Okay? Just remember that it's possible to have all VTEPs deployed on physical switches and create a form of an overlay network, which I showed you in the diagram. That form of an overlay network is called a network overlay. When you have VTEPs deployed on V switches, this is called a host overlay. Okay? And when you have some VTEPs deployed on physical switches, others deployed on V switches, you are creating an overlay network that's actually a hybrid overlay network. Okay? So these are just some terms which people use in literature, crafting a network overlay, crafting a host overlay, creating a hybrid overlay. I'm not going to use these terms in my course or any of the remainder sessions, so you don't need to remember it. Just remember that all these configurations are possible. VXLAN is a very flexible protocol. It can enable different forms of overlay networks to get created. Okay? And VTEPs are functions. It doesn't matter whether that function is implemented in a virtual switch or whether it's implemented on a physical. Okay, so I'll stop here. I've already said that VXLAN also has a control plane, but more on that later. First, I will talk about the data center network control plane, which is the routing protocols used in the underlay data center network. And then I will talk about the VXLAN control plane. And those two questions we will answer. How does traffic get routed in the data center network from source VTEP to destination VTEP? And then the second part of the question, how does the source VTEP even know what is the destination VTEP given the destination VM? By the end of this session, where I talk about control planes in the data center network, this part will get answered. Okay, so today we talked about VXLAN and how it implements the NVO3 technology and how this is the protocol that we use in most modern data center networks. Okay, that's all for today. Thank you everyone for joining in. I mean, I know it's festive season and on a Sunday we are having a class in the midst of a festive season. Thank you for joining. Have a good time with your families over this festival season. I hope you get some break. Happy Diwali, everyone. And I'll see you again next Sunday. Thank you. Bye-bye.